All right. Hello, everybody. Thank you for joining our webinar today. Looking forward to it. We're going to be discussing all about RTK and high accuracy GNSS and different applications and kind of demystifying it. Um, I think we're just going to first kind of just start it off with a poll of kind of who's here today. So if we want to throw up the poll and um, answer those questions, then we'll get kind of an idea of who we're talking to. Uh, So to start off, I am Tyler Gakstatter, and I'm a project engineer for Digital Mapping Group. We've been around since the early 2000s, selling and integrating, high accuracy GNSS. And we've worked with a lot of different companies, a lot of utilities, municipalities, agriculture companies, a variety of customers and use cases for this technology. And so we have a lot of information to share with you today. It's going to be, our approach is educational. So try to, really just teach you guys about the current state of the technology, what is doable today, and kind of what are the costs, and some interesting use cases. So I'm going to share my screen here. Okay, so we'll give maybe a minute or so to answer the poll. But this presentation is going to be all about demystifying RTK GNSS, and we're going to kind of go through an agenda, if you will, and we'll try to stick to it as much as possible. I may stray a little bit, but that's okay. So first, I'm going to kind of introduce myself and my role and kind of what I've done in my career in GNSS, and then we're going to do just some general background GNSS information, right? So in order to set the stage for a discussion about RTK, that relies on GPS and GNSS technology, we're going to look at what is GNSS. Then we're going to look at some applications of high accuracy GNSS, and then start diving into really what RTK is and how does it work, what's the state of it today, what are some maybe gotchas that you may not understand, and some infrastructure that's out there today that allows us to use RTK easier, and look at kind of operating our own RTK network or our own RTK stations. These are things that might be sound intimidating or sound prohibitively expensive, um, as well as mobile base stations. But we're going to take a look at that and what are the benefits and maybe why are some reasons you would do that. And I'm going to end it on a kind of a live demo. So I'm going to have an RTK receiver operating behind me outside, and I will share my screen on my mobile device, and we'll kind of start RTK and look at how a GNSS receiver responds to RTK and actually use it in a common mapping application from Esri, so field maps. So why don't we look at the results of that poll? Okay, we got a lot of local government and state government. That's not too surprising. That's the perfect demographic for this presentation. And of course, mostly United States, which is great. So thank you guys for attending. Hopefully I can teach you something today, and definitely don't be shy about asking questions. I'm gonna refrain from answering them probably until the end, but feel free to ask it at any time. Um, and even if it's just a generic GNSS GPS question or anything about high accuracy mobile data collection, kind of you can send my way and I'll answer it. So let's dive in. So I'm Tyler Gakstatter, and I've been working in this industry for a little over 10 years now. Um, and I have many roles or had many roles over those 10 years. So I've been I kind of have expertise in multiple areas, which allows me to see things a little bit differently. I'm not narrowly focused on just the GNSS technology, but how it's actually applied and used in an organization as part of a larger data collection effort, right? And that requires knowledge in multiple areas. So it's not just the GNSS technology, but how does that data that's captured from the GNSS receivers, how is that communicated and stored into an organization, into a system of record, into a GIS, which is most commonly where people are storing their GNSS data. So I have a lot of experience with the Esri mobile apps. Started using ArcGIS Collector when it first came out and watched it progress all the way to field maps and what it is today, which is actually a great high accuracy GNSS tool. And so that's why I'm going to use it as my demo application today. And I've also been involved in mobile development with some of our own internal data collection apps. And I have a lot of experience in IT and web applications and networks and a lot of the stuff which is required for achieving a full RTK solution, which we'll look at here today. So being in the industry 10 plus years, it's also a bit in the family. My father worked in the industry in the 90s, and so I kind of grew up around it. So even though my background was originally in kind of software and IT, I naturally kind of had uh, that GNSS knowledge that I just grew up with and continued to develop over my career. So that means I've seen a lot of the not just the new GNSS technology, but the old stuff too, right? I've seen the full systems and the backpacks that was 30 pounds that you had to carry around all day and setting up base stations locally on a site. Um, and so yeah, we'll hit on that stuff a little bit later. So kind of first start at why do we use this technology and what are some good use cases? So a lot of you are in local government, state governments, a lot of municipalities. We work a lot of utilities, water, gas, electric utilities, and these are industries that are, it's a natural fit for GNSS technology because it has distributed infrastructure, some underground, some above ground, but mostly outside, which is where GPS, works. Um, doesn't work inside, unfortunately, but and so distributed infrastructure that you need to manage, right? And so asset management is a huge, primary application for GPS and GNSS technology. Um, and over the years, it's, a lot of these companies have had a GIS or some representation, some map of their infrastructure, but it's a lot of it hasn't been accurate, right? Not accurate to the level that they need when maybe things go wrong or they need to do some analysis on the network. And so over the last couple decades, that technology and accessibility to that technology has become better, easier, cheaper. And so these industries and companies can leverage this higher accuracy equipment to maintain a more precise and accurate database or digital twin or map or representation of their infrastructure, and not only just map it once, but keep it up to date and regularly update their system so they can have a fine detailed view of their system currently. So asset management is a huge application. um, there's others as well. Drones became very popular in the last, geez, almost a decade now. And RTK and GNSS is a big part of that, right? Drones are their primary use is it's a flying kind of machine with a camera essentially, and it does photogrammetry and taking multiple pictures and stitching them together. It gives you an image, but you need to tie that down to a real world coordinate system, and the only way to do that, not the only way, but the most efficient way to do that is to use GPS in real time as you're flying a mission, and so that each image is geo-referenced to a known coordinate system that then you can lay your other data on top of. So data of your water system, gas system, maybe of your fields, right? If you're doing agriculture, and then you can start stacking that GIS data, and you get your everything kind of lines up. There's also some other kind of nichier use cases in industries, but hydrographic surveying is maybe smaller than asset management, but it's still widely used. And so that's combining a GPS receiver with a depth sensor, and then putting on a boat and driving it around a lake or some body of water, and so that you could map get a 3D representation of underneath the water, right, of the lake bed, river bed, whatever it be. Machine control on construction, vehicles. excavators, that kind of thing. GPS is also used, high accuracy GPS. And then some of the kind of the older use cases for it, civil engineering and surveying, right? And especially RTK, what we're talking about today. I think most people associate RTK with surveying. And it's kind of maybe in some senses, people think of it as reserved for being used with surveyors only. And so in the last, you know, definitely 10 years, maybe 20 years, a lot of people, including ourselves, have been trying to kind of break that mold. And, as prices come down on this technology, it becomes more accessible, easier to use. It's not only reserved for surveying, it's a very great technology. And, if you imagine having a centimeter level position for anything, there's a lot of applications that can come out of that. And so it's not just reserved for, construction sites and property boundaries and your kind of typical survey use cases. So those are kind of the applications that we're talking about that we use all of this stuff for. I'm guessing that applies to I touched on something that applies to most of you. But if you have other interesting use cases, I'm always looking for those as well. So this industry, like a lot of technology industries, there's a lot of acronyms, and it can get confusing and um, hard to track. And you've probably heard these buzzwords and kind of things around and may have some of understanding of what they are. But also a lot of times people will use them interchangeably and not necessarily when they should. And so it's kind of confusing about what each term really means, right? And so there's a ton of them. I can't go over all of them today, but I'm going to hit on some of them here, which is kind of barely scratching the surface, and then I'll refer to them and try to keep it clear throughout the presentation. So the one we're talking about today is RTK. RTK is a technology used to correct a position coming from a GPS receiver that allows you to get down to centimeter level ultimately, and that can vary a little bit, but that's kind of just boiling it down. And so there's a lot that goes into that, which is what this presentation is about. But whenever you hear RTK, that's about using that technology to get a centimeter level position. And the key to that is real time, right? So you're getting that position second by second, real time in the field. It's not post processing. There's a different term for that. That's PPK. And it's actually kind of the same technology, the same result, but RTK being done real time in the field, you're getting a centimeter level position from the receiver, whereas PPK, you're collecting data, raw data, so that you can process it later in the office and get that centimeter level position. So that's RTK. GPS, probably the most recognizable term in the whole presentation, is the global positioning system. But the important distinction is that is the US, United States constellation only. So it was the first one, which is why they call it global positioning system, right? Um, and its success was, pretty obvious over the decade or two after it was, installed and used. And so other countries recognized that and started to integrate their own. And so we'll look at that, and there's four major constellations. And so when we're talking about all four of them as a whole system, that's what we refer to as GNSS. And so that's the GNSS is going to be the blanket term. GPS is going to be a specific constellation of satellites. So they're all orbiting the Earth, but they're just owned and operated by different countries. Frequency. So satellites are broadcasting signals on various frequencies. There's a range of bands that are allocated for positioning, GPS positioning, GNSS, and so there are multiple bands. They're all kind of within the same range, but when we talk about frequencies, those are the kind of the distinction between the two. So there's L1 was kind of the first one. We have L2 and L5, and then also Beidou, which is the Chinese constellation, has one, and Galileo. So when we talk about frequencies, that's what it is, right? There's some receivers that only support one frequency. Back in the day, that's all they had. But as technology progressed, there's receivers that support multiple frequencies. The signal is the actual signal that's transmitted on that frequency. So essentially, these satellites are sending out signals on a frequency with a timestamp of when it was sent, so that any receiver on the surface of the Earth can receive that signal, well, multiple signals from different satellites, and use that timestamp to generate a position, calculate a position, kind of like triangulation. And then the last one, RTCM, that is going to be related to RTK, and that's a specific protocol that the data is transmitted in. So there's many different protocols. RTCM is the open format. So any RTK receiver should be able to consume that and use it. There are other proprietary protocols that within, manufacture specific networks, they will have their own that have different, various benefits. Okay, so just generally, when we talk about GNSS, we have those four major constellations. We have GPS, which is the US constellation. It's made up of about 31 active satellites. More than 31 have been launched and deployed and used in the system, but there's only 31 active at any time. And that orbits the entire Earth, right? So as the satellite is orbiting the Earth, depending on where you're at on the surface of the Earth, you might be able to see the satellite or you might not. It might be on the other side or it might be too low on the horizon. In that case, you won't be able to use it. But if it's generally above your head, then the receiver will be able to use it. So it's kind of line of sight. But it's not just because it's operated by the US, it's not isolated to users in the US. And that's same with GLONASS. The GLONASS was kind of the second major constellation to be in use, and that was owned and operated by Russia. They have about 24, that may be higher now. They have about 24 satellites active. And so for a while, in the 2000s, they were early 2000s, those were the two main constellations, really the only ones. Just in the last 10 years or so, did these last two come into play, which is Galileo, which is the European Union. They have a constellation of 24 satellites that also fully orbit the Earth. And Beidou, they have quite a bit more. They have 35 plus satellites and that also orbit the Earth. There was a time, and there actually may be some satellites, I'm not sure, that they actually programmed and designed to or do like a figure 8 orbit just above China, so it would only be available to them, which is kind of an interesting implementation of that. But we have receivers that will use the Beidou satellites all the time, and so they have plenty of satellites that will orbit the whole globe. Um, and so when we're going to get more in detail on this, but generally speaking, if you have an older GPS receiver, then it may only support certain constellations. So it may only, kind of at the extreme now, maybe there's a receiver that only supports GPS. Got one that you've had a really long time, could only support GPS satellites. And in that case, you're going to be quite limited in kind of where you can get accurate positions. So representation of that is on the left. This diagram here is what we call a sky plot. It's a representation of the satellites that are in view and used by a GPS receiver. And so this one you can see is only using GPS satellites. And this is pretty common even now. About you'll have 11 to 15 maybe in view, and using a subset of that. So in this case, it has 11 satellites in view on the right side of that slash, and then you have 9 in use, being it's actually using 9 in its position to generate its position. And GPS isn't a perfect technology. You can't receive those signals anywhere. They're actually quite weak. And they'll be blocked by buildings, trees, leaves, other vegetation, vehicles, yourself, right? So if you have a handheld GPS receiver, you're holding it down kind of by your chest, like your body will be blocking all the signals behind you. And so it becomes increasingly important to have access to as many satellites as possible, right? And so having receivers that are able to track all 4 constellations really gives you the upper hand and allows you to get accurate positions in more places where there are those obstructions. So on the picture on the right, you can see total sats in the upper right of that image. 32 are being used out of 48 total. So you can imagine when you start getting into some trickier areas under trees, that kind of thing. Some of those satellites will drop out. You won't be using 32 anymore, but because you've got so many to choose from, the receiver can pick the best satellites that are still in view unblocked, and you can still get a good position. Whereas the one on the left is a lot more fragile. So this is something to keep in mind as we talk about base stations with RTK and then different types of receivers and their ability to get accurate positions. Okay, GNSS corrections. So we're still kind of in the background part of this presentation, right? This is like GNSS in general. We're getting closer to the specific topic of RTK, but this is generically GNSS corrections. And so let's first start without corrections. So a GPS receiver, even with today's technology, spend as much as you want on the GPS receiver. It can only get a position of maybe 1 to 2 meters accuracy without some sort of correction source, right? Any GPS receiver, spend any amount of money, but if you don't have a correction source for that receiver, just operating on its own, detecting satellite signals and computing a position, 1 to 2 meters, uh, which is okay for a lot of applications, for non-professional applications, for just applications that don't require a high level of accuracy. That's fine, and there are receivers that you can buy that are it's what we call autonomous. It doesn't use any correction source at all. But to get lower than that, any level lower than that, there are multiple levels, which I'll describe here in the next slide. You need some sort of correction coming from um, a base station or a collection of base stations. And this is not just limited to RTK. So, I mean, some of you who are familiar with RTK already probably know that there's a base station involved or a network of base stations. But there's other correction sources that aren't RTK, but they still use a base station or a collection of base stations to generate that correction that is consumed by the rover, right? So we'll look at some of those specifically, and specifically the ones in the United States that are available. But in general, you have a base station or collection of base stations that is generating a correction that is then broadcasted to the rover, and rover being the GPS receiver that's in your hand in the field and that you're using to collect positions. And there's different means to get that correction from the base station or base station network to the rover. And there's three primary ones. First one listed there is satellite, and these are different satellites than positioning satellites. So positioning satellites are orbiting the Earth and just broadcasting satellite signals with timestamps, kind of one-way communication, right? The receiver receives it and calculates a position on its own. These other satellites are communication satellites. So they have maybe a base station, network of base stations, on the ground, and then there's a computer server that generates the correction and streams that through a communication satellite that your GPS receiver can access by communicating with that satellite and receiving the correction, but it's separate from positioning. So satellite-based corrections, that's what we're talking about, right? Where you're receiving a correction over the satellite in some way. Internet, which is a probably pretty obvious one these days, where you have those terrestrial base stations. They're connected to the internet network, to servers that are accessible over the internet through a rover directly, or through like a mobile device that's connected to a rover. Just internet being used to communicate those corrections from the base to the rover. That's the most common today. And then there's radio, so terrestrial radio. Most commonly UHF radios. So in this case, if we're just looking this one-to-one, where there's one base station on the left, broadcasting to the rover on the right, the base station would be equipped with a UHF radio transmitting the GNSS corrections at once a second. And then the rover would also have a UHF receiver radio that it's integrated with that would be receiving the correction from the base station. Um, this was the primary means of communication between base and rovers, before the internet was ubiquitous. So people would take a full, base station GPS receiver, UHF radio, everything out into the field, set it up maybe even just for the day, or short, temporary time span, and then they'd have the rover also with UHF radio, to receive the signals, and they'd go out, collect their data, and then break down the base station, the rover. And that's, you can imagine that's a lot of equipment, but that's how it was done for a long time. Still is done today in certain scenarios. So those are really the primary means of communication, right, for these corrections, either over satellite, over the internet, which is probably preferred by most people now, or the radio. And it's still used today when you don't have internet. There's a lot of data collection efforts that are done out in the middle of nowhere. There's no connectivity. Okay, so let's look at a couple of the different levels of accuracy, right? So starting at the top, consumer grade, 2 to 4 meters. This is usually GPS receivers that are in autonomous mode, so they're not even using corrections. And they're probably not even very high quality GPS receivers or GPS antennas, right? Just because their use cases aren't, they don't need high accuracy. And probably the best example today of these are your phones, right? Your mobile phones, tablets, maybe your car has built-in GPS. And you might think that they need very accurate positions in your cars for navigation in your phones, and navigating you to Starbucks or your friend's house or whatever. And they appear to be quite accurate just in your experience, because it's shows you exactly where you are on the road, in the middle, and exactly where to turn and all this stuff. But um, they're not just leveraging the GPS position for that. For that experience, it's also they have these roads that are mapped. So your GPS may be reporting a position that's kind of near that road, and it'll snap your position to the road. And so it's kind of combining these different technologies and pieces of information to provide you with that seamless, like seemingly accurate position. So that's consumer grade. Then recreational grade would be something like this. This is a little mobile mapper. Um, there's a lot of other ones like these, like Garmin's, that are used for hiking and that kind of thing. And 2 to 4 meters for that is great, right? You just want to not get lost. So 2 to 4 meters is plenty. You have your position on a topo map, and you can see, where you've been and how to get out of there. Uh, Sub-meter grade is when we start to break that 1 meter mark. So a GPS receiver that can reliably get you a position under a meter. Um, and this is when we start to get into professional grade receivers. And the price jump between consumer, recreational, and sub-meter and beyond can be quite significant. I think that gap is closing, but still, recreational grade is hundreds of dollars, and sub-meter can be, for reliable professional grade sub-meter receiver, it can be in thousands. And so this is probably the biggest, one of the biggest jumps there in pricing. But these receivers are focused and specifically designed on getting you reliable GPS positions under a meter in a lot of environments. Not everywhere, but in forestry environments and places where there may be obstructions in satellite signals. They make the extra effort not only in the firmware that they're running, but in the hardware that they're using. So hardware using for the antenna, hardware that they're using for the signal processing. They have usually bigger batteries to support that, and so they're the devices on their own. Um, they usually today Bluetooth to a mobile device or a computer that does the rest of the kind of data collection. But these receivers are standalone, purpose built for getting you sub-meter positions. And in order to get under a meter, right, we need a GNSS correction. And so these are usually using satellite-based systems. So that term there, another acronym, SBAS, is satellite-based augmentation system. That's a blanket term for these satellite-based correction services. And the term on the right, WAS, wide angle augmentation system is the US specific system created by the FAA to track airplanes. And so it's a basically it's a system of terrestrial base stations across the US and maybe even Canada and some other countries, Mexico. And it has that larger system creates essentially one correction or some really broad corrections to serve a large area. So they'll serve the entire North America plus some. And that's served over a communication satellite that most receivers today, even your iPhone, can consume and get that GNSS correction to feed to the GNSS receiver that will allow it to get under a meter. Um, and the performance of that is not necessarily dependent on the WAS system itself, but on the receiver that is leveraging that correction, right? So there's different ways to apply that correction, and some manufacturers do better than others. Some products do better than others. I've seen some receivers get down to close to a foot level of accuracy with WAS, which is pretty great for a free service that's just available and don't need internet for or anything. But it depends. It can range from that to a foot all the way up to a meter, kind of depending on the day and how it was implemented in the receiver. The next level is actually kind of a non-existent category in a way, and that is the decimeter grade, which is over my career of whenever I ask people kind of what accuracy they need, if they're in kind of the high accuracy space, they often say a foot, right? That's a very common um, kind of range of accuracy that people want. And it's interesting because the technology just there's kind of a big jump. You either have sub-meter, which yeah, maybe you can kind of approach getting down to a foot, not necessarily reliably, or you use RTK, which we'll talk about next, that gets you down to centimeter level, and that's a pretty big gap, right? The sub-foot or foot level is right in between there. But you're either using a satellite-based, correction service like WAS that gets you sub-meter, or you're doing RTK, which snaps you down to a centimeter. And so there's really actually not a whole lot of in between. There are manufacturers over the years that have kind of created this category by taking an RTK receiver, RTK capable receiver, and requiring that it actually connects to an RTK base station or network, but they kind of cut it at the knees and they don't let the receiver output a centimeter low position. They either only let it float, for those of you who are familiar with that term, or they do some other apply some other algorithm that just doesn't allow it to output a centimeter low position, even though it's actually computing one at some level. Um, so that's kind of an interesting category. There are other services that have come about, like satellite-based services that are not true RTK, but they will give you an RTK fixed position, but they'll be around kind of the 10 centimeter foot range. Galileo high accuracy system is one of those, and other satellite-based correction services that are provided by the manufacturers. So those are kind of in that range too. Okay, the last one, the most accurate is survey grade. It's usually referred to it as that. This is using RTK, right? And 1 to 2 centimeters level of accuracy. Um, that can vary a bit depending on other factors, which we'll talk about. But this is as good as it gets, right? This is high-end GPS receivers that are RTK enabled. These are typically, $10,000 or more. There are some options that are less than that, but just generally you're looking at around the $10,000 range. Um, and it's probably as good as the GPS technology is going to get. I mean, there's a lot of things that you can do to squeeze a little more out of it and get down to even less than a centimeter. But generally speaking, if you're using it across a large area, across a whole city, like you're mapping a water system or something like that, you're getting centimeter level accuracy. Could be up to 4 centimeters, 5 centimeters, 6 centimeters, depending on where you're at, what kind of obstructions your GPS receiver has, how close the base station is, that kind of thing. But um, this has been around for since the 90s, mid 90s. We were able to get centimeter level accuracy back then, right, which is pretty impressive. And so the things that have developed over the years that have made it better have been more satellites available, right? I remember people having to just literally sit there and they want to capture a sprinkler head or something like that, and there's just not enough satellites overhead to be able to get an RTK position. So you really have to wait there for 10 minutes, 20 minutes in order for the satellites to position correctly so the receiver can receive the signals to get that centimeter level accuracy. So a lot of more satellites have been launched and been integrated into the GNSS system now. And so you can go out today at any time and not have to worry about, is this the right time? Are a certain number of satellites above to be able to get a position? So you can get RTK in more places at more times. And then also additional frequencies we'll talk about because that's kind of one of the gotchas of RTK. But single frequency RTK, which is the original implementation, it can get you centimeter level positions, but it's a more fragile and takes longer, kind of thing. Okay, so RTK sub-inch accuracy technology requires a base station or network of base stations in near proximity to your GPS rover, so where you're using it. If you're using a single base, so communicating directly to a base station, um, that baseline, which is the term we use to say like how far away, what is the distance between the base station and rover, right? Um, that will determine the level of precision that your rover is able to achieve. So if you have a single base station and you are 15 kilometers away, you'll be able to achieve, centimeter level accuracy. The further out you go from that, and it kind of just tapers off, right? It's not a binary thing, but the further away you get from that base station, the less precise your rover positions will be. Just to give you some kind of idea, basically out to 20 kilometers, I think, is about a centimeter, and then every uh, 10 kilometers after that is an additional centimeter. Um, Again, very dependent on where the rover is at, if it's open sky, how far it is away, that just the performance of the receiver itself, the multi-constellation. Um, but these days, with all of, if you're tracking all four constellations, all frequencies, you can achieve some pretty impressive results from a large distance from base station. Even like 80 miles away, you can still be under like 10 centimeters, just to give you kind of some rough numbers. But baseline is an important factor in RTK. Um, so it's dependent on the distance between base station and rover. Uh, but it doesn't have to be just one to one. You can have one base station serve corrections to any number of rovers, right? That correction that's generated by the base station is generated once a second, and it can be applied to at the extreme, millions of rovers, right? Now, usually it's not that because there's not that many people out in the field using that many rovers on a single base station because it can only serve a fairly small area, right? Let's just call it like a city, kind of that level of radius, and and then also it's the limitations of communication, right? So if you're on radio, obviously you're not going to be able to communicate to that many rovers. Internet has opened that up, so basically any rover on the internet can connect that base station. But again, it kind of goes back to the base station can only serve a relatively small area, right? But that correction is able to be used by any rover. That's the important piece there. And it can be used with any type of rover, right? The base station is a Trimble base station, right? That correction, as long as it's in the open format RTCM3, it can be used with any manufacturer's receiver. So you can mix and match those manufacturers, um, no problem, right? As long as things are configured correctly. Um, Another thing to note is that the base station it will always be the weakest link in that whole system, right? Which is important to have the best technology in the base station possible and the best view of the sky and all those things, right? So it's very important that base station is operating an ideal environment as latest technology. For example, earlier when I was talking about GPS versus GNSS, right? So a receiver that can only track GPS satellites versus one that can track all four constellations. Well, you want your rover to be able to track all four constellations, but you also need your base station to track all four constellations. If you have a receiver that can track all four and you connect to a base station that can only track GPS, your rover will only be able to use GPS satellites when it's connected to that base station. And this was it's gotten better these days, but let's go back 10 years ago, even 5 years ago, there were quite a few base stations out there, existing networks that were operating bases that were limited in the constellations that they supported. And so CRTN, that's the California network. It's kind of a collection of many stations operated by different people. And so you had a large variety of hardware in that system. And a lot of them were GPS only, just because they were older stations, it was older hardware. And so it was, CRTN is great because it's free. But when you connected to it with your brand new GPS receiver that you paid good money for to have four constellation support and all frequencies, as soon as you connected to that base station, your receiver is now operating like one, that was bought a decade ago or more. It's GPS only satellites. And you'll notice that it really struggles out in the more difficult environments. Sure, if it's in the open sky environment, probably be fine. Probably won't notice anything. Accuracy is great. Hold on to that fix, no problem. But as soon as you start to go, near trees and kind of in urban canyons next to buildings, it falls apart really quickly. Even though your receiver is fully capable of maintaining better positions in those areas, the base station is limiting the performance of that rover. And so the basically the quality and the technology in the base station becomes the weakest link as a part of that whole system. It's also important that the data being communicated between the base station rover is consistent. It's not a lot of data. You can think of it as kind of if you can imagine, it's just trickling data from the base station to the rover. It's for those of you that kind of understand the units of bandwidth, that kind of thing. It's about 3 MB of data total per hour between a base station rover. And obviously that varies depending on the protocol and all that being used, number of constellations too. But it's not a lot of data. What is important though is that the rover is receiving that correction every second from the base station. So 1 hertz, right? And GPS receivers have an indicator that they'll display to you if you know where to look that will tell you how many seconds it's been since it's last received that correction from the base station. And it's commonly referred to as diff age or some type of age. And it's just an integer. And as long as you're connected to a base station and it's receiving corrections at the regular interval, that value will be 1. That's the lowest it can get and what you want it to be, which means it's been 1 second since it last received a correction from the base station. If that number starts to climb, that means for whatever reason, your rover had stopped receiving corrections from the base station. So maybe if you're connected over the internet, it's a network issue, or a radio, maybe you got out of range, right? And so if it starts to climb, then the rover will continue to use the last correction that it received from the base station for as long as possible, right? But the problem is that what that correction is it's a representation of the ionospheric conditions in that area, right? So that's what a base station is doing. It's generating correction that allows the rover to calculate out or fix the anomalies that are created in the GPS signals coming from the satellites through the ionosphere. And so that means that the conditions between the ionospheric conditions between the base station and rover need to be similar, right? And those conditions change; they're dynamic, and that's why we need correction every second. So if you have an old correction, let's say that's 60 seconds old, well, those ionospheric conditions have changed. They're affecting the signals differently now. So even though it's applying that correction, it's no longer as effective with the current conditions. And so you'll see your accuracy. I mean, your accuracy won't it won't just blow up right away. It'll start to kind of trickle down, and and your position will get worse and worse over time until you start receiving those corrections again. And when you receive the next correction, then you'll see it go back, right? It'll that accuracy will tighten back up, and all of your stats will look great. So you need the baseline to be short so that the ionospheric conditions are equivalent between the base and rover, and you need regular and consistent corrections being broadcasted from the base received by the rover. Okay, single frequency versus multi-frequency. This is one of the gotchas that I've been referring to, and it's kind of confusing out there if you don't know what you're doing or if you don't have experience with RTK before. And so there's a lot of GPS receivers out there, a lot coming from China and other countries that are enticing because they're cheap, right? They're affordable, it's accessible, it's on a spec sheet, they look equivalent to a lot of the other more expensive receivers. And this is one of those spec sheet items that can kind of trip people up. And so single frequency RTK is also referred to L1 RTK because L1 is that first frequency. And that was the original implementation in the mid 90s. And it was single frequency RTK. You can get centimeter level positions. So right, that's going to look good on the spec sheet. It's capable, right? But it requires a ideal environment, requires ideal conditions. And so you need to have open sky because it's more sensitive to trees and buildings and other obstructions. It also requires that the base and rover are much closer to each other. So you can't get as far from the base as you could with multi-frequency RTK. And even with the ideal conditions, it takes longer to get a what we call RTK fixed position, which is okay, I've got centimeter level position now. I'm using those corrections, applying them, got centimeter level position. It takes a lot longer to even get that even in the ideal conditions, right? So back then when that was the only way, it was worth waiting. You don't mind, like I talked about earlier, like sitting on the sprinkler head and waiting for 10 minutes to get a RTK position because that was really the only way to do it. Um, Nowadays, with extra investment, of course, I mean the better receivers and better hardware are more expensive, but they save more time. I mean, if you put a multi-frequency RTK receiver and a single frequency RTK receiver side by side, what you're going to notice is that the multi-frequency RTK receiver fixes in seconds. So as soon as I connect to an RTK network with that multi-frequency receiver, it's going to go to an RTK fixed position. And it's also going to hold on to it better, more often in tougher environments. Whereas the single frequency RTK, you'll start the correction. So my single frequency RTK receiver is receiving the corrections from the base at regular intervals. It's starting to fix those anomalies but after minutes it will fix. And so that's okay in certain scenarios if you're not collecting much data in a single day, you're just grabbing a few points, then maybe cheaper hardware single frequency RTK is okay. But if you're doing production mapping, you're collecting many points a day, hundreds of points a day. It would be a very frustrating experience. Uh, as it was back in the 90s, it was frustrating, but that was the only way to do it. So it didn't seem as frustrating, right? Whereas today, if you watch those two different pieces of hardware side by side, it's pretty obvious. And over the lifespan of the receiver, spending the extra money to get the multi-frequency RTK with the 4 constellation support is going to save you money over time, right? It's kind of the capital expense initially that's more, but the operating expense is going to be less because your field workers will be able to, be very productive, right? They can just go out there, turn it on, connect RTK, got a position, grab it, and go. So if you're going to do our L1 RTK only, I definitely recommend you try it before you buy it, or just consider those factors. Okay, we touched on this a little bit. I'll just keep this one kind of brief, but our communication options for RTK. Radio was kind of the first one, right? Because it's RTK mid 90s, internet wasn't really out there yet. I'm sure it was there, but most devices weren't connected regularly. especially out in the field. And so you use just local radio transmission, right? So you'd be on a small site, fairly small site, set up a base. You'd be operating your rover within, a few miles of it, and that's it. If you needed to capture data elsewhere, you'd tear down the base, move it, set it up somewhere else. Still an option today. We still provide customers with that solution. Still works well, and it's actually a consistent solution. We'll talk about that later, but definitely less common these days. Internet by far the most common use for these communications because almost everything is connected these days to the internet, right? Either cellular networks or broadband, at your office. Um, it just allows everything to be connected. But those are also limited, right? There are areas where you can't get cell coverage, and a lot of the times people are collecting data there. And so, kind of a relatively new development that we've all heard of Starlink, and I think Amazon's starting their own now, and there's other options out there. But these low Earth orbit satellites that are providing kind of blanket coverage for internet. Um, I've used Starlink out in the field, and pretty much, it's actually similar to GPS in a way where, if you have trees and heavy tree canopy or that kind of thing around, it's going to struggle because it is satellite signals really that it's receiving, even if it is a little different than GPS. But if you have an open view of the sky, you can take a Starlink device out there and get, impressively fast internet, which is totally, uh, usable with RTK. Like I said, RTK doesn't require a lot of data, a lot of bandwidth. And so this is relatively new, can be used. Base stations can be outfitted with Starlink, and so can rovers. I actually have a T-Mobile phone, and they've partnered with Starlink, and so they have some limited features available now. So I can go out and actually send a text message using Starlink. And I believe next month in July they're going to roll out data service, and so we're going to be testing that out as a option for RTK because that really opens up kind of these opens up the options that you have for using RTK and getting RTK corrections in these disconnected environments. So I think there's going to be a little bit of a shift in that area. Okay, what does an RTK receiver look like? There's a lot of different ones, right? We've got I have some here. This is a handheld RTK receiver. This is one of the newer technologies. I'm sure a lot of you are familiar with the yellow device. I think this is kind of blanking it out, but the yellow Trimble handhelds, those were very popular in, kind of the later 2000s. Still a lot of them out there. And even back in the day, they had these older, mobile rugged devices. So they take a lot of different um, form factors. Typically, what you're gonna think of when you think of RTK is something on top of a range pole, right? So like something like this, it's Trimble maybe R10, and or like this. These are common RTK, uses for centimeter level accuracy. But these days, they're typically something on top of a pole and Bluetooth enabled, right? So you've got really three components. You've got the RTK GNSS receiver, you've got the mobile device to collect the data, so Bluetooth connection between this mobile device and the GPS receiver, and then you got the data collection software, which that really opened up in the last 10 years, right? With iOS and Android having these app stores where anybody can really create a GIS data collection app. Some are executed better than others, but there's plenty of options out there. Why can't you just use your phone or tablet for RTK? Maybe we'll get there eventually, but really what it boils down to is that these manufacturers are very sensitive about what they put in these phones for what uses battery life, how much space does it take up, and is it really needed, right? And so, like I said before, with navigating to Starbucks, friend's house, whatever, it doesn't require centimeter level accuracy. So there isn't enough of a need for them to prioritize that level of precision. So even though it may be doable today, um, there's no need for it yet. And it doesn't look like it's coming anytime soon, but I do see it going that direction. In fact, some of these phones and tablets have like the chip in there that is capable of RTK. but they don't have the right antenna, right? Because the antenna in these is basically just an etch on a board. It's not a dedicated, GNSS antenna. It's obviously much larger that you couldn't fit into a phone. Um, and they're not willing to give up the extra computing power and battery required to run it. And so even though, people have used their devices and gotten relatively accurate positions, usually in cities, um, it's not reliable, and they're not just using GPS. They're using GPS, Wi-Fi networks, Bluetooth, kind of all this stuff. It's like augmented GPS to try to get you the best position possible. They want to get you a position as fast as possible that's like generally accurate, right? Accurate enough to navigate you places. Okay, why invest in RTK? That's also another probably common question in people's heads is, even though prices are coming down, it's still an investment, still thousands of dollars. Um, and kind of the argument for that is that the kind of the capital expense versus operation expense, in a way where it's an investment up front, but it doesn't require any more time to collect that data, and the accuracy of the data you're getting out of it is so much better that as technology develops, more analysis tools become available. You need to have accurate data to be able to feed into those systems, right? And so if you're, a big proponent of going out to collect data, collect as much data as you can and as best data as you can. And so if you're doing a large effort to collect data, map a whole water system, gas system, electric system, anything like that, and you go out there with sub-meter equipment, maybe that's okay now, but maybe in 5 years when you start using different applications, that data is no longer usable, and you're going to have to do another effort to go out and kind of tighten up that data. Also consider that most of the time people are collecting data so that they can navigate back to it and find it, right? So, and a lot of stuff is underground. Let's just take a water system, for example. You've got a valve underground, maybe buried, maybe not so obvious where it is just by looking. Um, if you use a sub-meter receiver to go capture it and a sub-meter receiver go back and navigate to it, now you're compounding that error, right? So if it's a half meter to capture it, half meter to navigate back to it. You're really at a meter when you try to go back and navigate. And maybe that's okay, and maybe that's not, but that's something to consider. Whereas if you go out and map it once with RTK, centimeter level, accuracy, it's highly unlikely that you're ever going to need to uh, recapture that asset at a high level of accuracy. When you're at centimeter level, actually capturing a water valve, it's not about can you find it. It's more about where on the valve should I capture it, right? Like I capture it on the top of the lid or on the side, or you know what I mean. It's more precise than you need, and likely will ever need for any type of analysis or navigation back to it or anything. So um, today with prices coming down, the accessibility of the hardware, RTK networks, it makes more sense now than ever to take that, do that extra investment, use RTK to capture um, your assets. Uh, okay, so in the future, just to give you guys an idea, kind of a bird's eye view of kind of where we're at. I think RTK has kind of reached its peak in a sense. I think we have four major constellations. That was the major development in the last 10 years. Going from GPS to now GPS, GLONASS, Galileo, Beidou. And that's unlikely to change. There's some talks. I think India has one in development, maybe one other country, but it's not going to get that much better, right? Pretty much you can go outside any time of the day, have plenty of satellites to get an RTK position. RTK is getting you down to centimeter level accuracy. Maybe some developments in GPS signals, being able to handle them better in trees, that kind of thing, but unlikely. So the future really isn't GPS getting better, more accurate, able to get centimeter level positions. Like I said, unlikely to need anything better than that. But it's getting it more places. And in order to do that, you need to do some type of sensor fusion. And so really the future looks like combining these RTK receivers with additional sensors. And that can look like laser rangefinders, right? So a lot of people, I mean, that's been around for a while in different ways, but using laser rangefinders to offset GPS positions, so standing somewhere where you can get a GPS position and shooting into, under tree canopy or inside buildings. LiDAR is a big one. This is EOS's latest GPS receiver that actually combines an RTK receiver here with a LiDAR sensor underneath and a tilt compensation sensor. So you got rid of the pole, you just use a LiDAR sensor, which is basically a laser pointer to map with RTK precision wherever you can point that laser. So that allows you not only to use it just easier in all environments, get rid of the pole, but you can capture data in places where maybe you can't access it, maybe over a fence or in the middle of the street while there's traffic. Also, you could kind of do an offset solution, so you can stand back where you can get a GPS position and shoot into a place where maybe you can't get as good of a GPS position. And I think there's going to be just more of that. There's going to be more integrations, sensor fusion with GPS. It's no longer just going to be just a GPS receiver getting as best a position as it can and using that in GIS. It's going to be augmented GPS. And that's going to require consistent and reliable RTK, right? So all that infrastructure we talked about with the base stations and how you get the corrections, that's going to become very important. Okay, let's look at a base station. This is one that we actually produce. This uses an EOS Aero Gold down here, bottom right, as the GNSS engine. And that can be used as a base station or rover, right? There's usually nothing special about the GPS receiver that's used as a base station. It's just a GPS engine that is, put into a different configuration to output corrections. So we're able to use this Aero Gold that looks like a rover. You could take this out and mount it to a pole and with an antenna, or you can put it into a base station like this. So the three major components are you got the GNSS engine, you've got this is the fast RTK module. This has basically a computer. It's a lightweight computer that interacts with the Aero Gold and broadcasts the corrections over that N-trip protocol, so over the internet. And so you can connect this base station to the internet, either directly to a existing network infrastructure or with a cellular modem, which is pictured here, this Cradlepoint device. And then, as many rovers as you want can connect to that base station and consume those corrections as long as they're within that radius, right? That service area of the base station. And there's a lot of base station out there. If you just search for base station hardware, there's a ton of them. And they all kind of do the same thing in a way. There's generate a correction and broadcast it. And so what becomes important is the software that's running them and what that allows you to do. It could be just a black box spitting out corrections that you connect to. But often when you deploy them into a kind of enterprise or close to enterprise environments, there's these other management tools that you need and troubleshooting tools that are helpful that the software really can help with. And so we've developed some software for this base station that I'll show you guys here in a minute. That allows you to really see what's going on with the base station. It's a good visual of what kind of how this RTK is working when you have a rover connected to a base station. Here's some examples of installations. So if you want to picture, if you've never seen a base station, kind of don't have an idea of what it looks like, this is there's lots of different types, but typically it's mounted on top of a roof of a building and or a water tower. Those are fairly common as well. It's because you want it to get up high so it doesn't have any obstructions. So in each of these pictures, you have the RTK base station box, which contains these components that we just looked at, and then the antenna. So here's the GNSS antenna here. Very important that it's mounted in sturdy fashion so it doesn't move or sway. If this, let's just talk about in the extreme, if this pole is swaying, right, any of the rovers that are connected to it, their positions will be directly affected by that antenna moving. They would actually see their positions also move. So very important that it's sturdy, doesn't move, and yeah, and so that's what a typical kind of base station installation looks like. They're in all types of different buildings, configurations. Sometimes the antenna is mounted up here, but the box is down in the server room. So you have, up to like 100-foot cable length that can connect those. Um, so, if you were connected to an RTK network and used it, you're probably using a correction that was generated by something like this nearby. Statewide network. So RTK is become quite popular over the last 20 years or so, and the big barrier to entry originally was access to a base station. So in the early 90s when it first came out, you have to set up your own base station, and that was pretty much your only option. Um, as different organizations started using them across large areas, it makes sense to set up RTK networks and sell subscriptions or maybe provide free access. And so in Oregon, which is where I'm from, the Department of Transportation put up their own network, so taxpayer kind of investment to put up their own network and provide corrections for free to all Oregon users. Um, that's not for every state. Some states have free networks like this. Other states have no network at all. Some states have networks and don't allow access, right? So it just depends. We created this tool to kind of look at the state of those networks. So this is a map of, and it doesn't have all of them, but statewide coverage of RTK base stations. So all these green states have statewide coverage. You can zoom in and kind of see all the stations that are available. Just to give you an idea of kind of like how many base stations are out there, right? If you don't know, it's probably a lot more than you expect. So California has a ton. Arizona's got a network. Utah, you can see this kind of a RTK desert here in the middle. But then over on the East Coast, they're pretty good with RTK networks as well. So if you're in one of those areas, the investment into an RTK system is a lot less too, right? Because you don't have to worry about operating your own station. You have something available to you potentially for free, right? Um, and so yeah, this is a neat tool and kind of gives you an idea of what's out there. Okay, so that brings me to the next point is, when or should you install your own RTK station? There's a lot of bases out there, a lot of networks that are available, some for free. And so in Oregon, it doesn't necessarily make sense always to set up your own station because it's free. They actually have pretty up-to-date hardware, which is good and in another point of consideration. But some states have networks, but they're private networks, right? And they charge subscriptions for them. And it's not uncommon for a subscription to cost $2,000 per receiver per year, right? Or $1,000 per receiver per year. And if you have any kind of larger organization or data collection effort, even if you have 5 receivers, that's $1,000 a year, that's 5,000 a year, as long as you use the network, right? And again, with technology, prices have come down, things have become more accessible, and base stations are, in the range that it makes sense to invest in one, right? And you invest in it for a few reasons, right? One, you control it. So if there's any downtime in a network that you're connecting to, you don't have any control over that. You control the operation of the base station if you own it. Also, if for organizations that are security conscious, want to kind of keep everything within their, behind their firewall, you can own and operate your own station that's just completely within your network. And if you want, you can open up and share access to that with other organizations or contractors. You can even sell subscriptions if you want. But you can also make sure that you have the latest technology. And that's probably one of the most important pieces to it. Make sure that your base station and rover have equivalent capabilities so that you're maximizing your accuracy and productivity out in the field. So you can get your own base station that supports all 4 constellations, all 3 frequencies. Get your rovers to do the same thing. And that way you're getting the best experience out in the field for the data collection, right? And base stations, they might seem intimidating, but really you can think of it as like almost like an IoT device, Internet of Things. The initial setup is, requires some just expertise. It doesn't take a lot of time. but just to make sure you know what you're doing, and you have to set reference coordinate properly. But once it's set up and operating, it's mostly maintenance free. Uh, you just let it run, and you just connect to it when they're ready to use the RTK, and that's pretty much it. And with the capital expense, it'll quickly pay for itself if you have even just 5 rovers, right? At $1,000 a year or more, for a private network, it starts to make sense, financial sense, really quick. Another option is mobile stations. So this you would get for different reasons, right? Um, this one was what I'm talking about here is a static base. So that would be something like this where it's permanently installed. If you're a municipality, a city, you can a lot of times get away with one station. So pick a building in kind of the middle of the city if you can, and set one up, and it will serve the whole city for as long as it's running. Um, but other use cases require you to be mobile. You're not always collecting data in the same spot. I've had some interesting customers over the years. I'll highlight one where they were going and mapping cemeteries, and that's a um, important kind of industry. And they go out and they travel all around the U.S., multiple states, East Coast to West Coast, and they'll do these big efforts where they capture all the data there and map it all out for a week or two at a time. And so it doesn't really make sense to put up a base station at those sites permanently, but it absolutely makes sense to have a mobile base station that you can take with you, set up while you're there, broadcast corrections, do your data collection effort, and then pack up and move on to somewhere else. And then you don't have to worry about, okay, does this state have a network that's accessible? Is it free? Do I need to get a subscription, manage the subscriptions, even sometimes deal with different datums that those bases are referenced to? It's a very consistent solution. So even though it requires this extra piece of hardware to transport and use, it's consistent RTK anywhere in the world. I could take this anywhere in the world, set a coordinate, and get an RTK position, centimeter level position, in a matter of minutes, right? If you have a known point. So very, very interesting solution for certain applications, including one I just described, or for just if you're just out in the middle of nowhere, there's no connectivity. This is almost one of your only options. And so both of these base station solutions are around $12,000. So whether it's the static base station here or the mobile, and so in certain scenarios, kind of as I've highlighted, that it makes financial sense pretty quickly, um, with that investment. Okay, so I'm gonna kind of wrap it up. We're at 11:15. That's about right. Wrap it up with a live demo for any of you that haven't used or seen RTK before. I'll show you kind of how quickly it's used, um, and how do you set it up, right? Like how do you actually use it, and how does that translate to a accurate position in field maps? So let's first go here. So this is our private network that we run, and this is the office that I'm currently in. And I have a RTK receiver behind me. And so I'm actually going to share my phone screen. See how smooth this is here. Excellent. Okay, so this is field maps. And this is our office and some data that I've collected here. And this is my current position, that I gave for my receiver. So typically with these GPS receivers, whether RTK or not, you'll have a manufacturer's app that communicates with that receiver and gives you detailed information, and allows you to connect to RTK bases. So this is EOS Tools Pro, which is I'm using an EOS Scotty receiver. And this is that app for these specific receivers, right? So this is giving me up-to-date, real-time information about the receiver. It doesn't collect data, but it's just reporting it in real time. And we're gonna look at some of the key factors that are key like indicators that you'd look at when you're doing general GPS data collection and what they look like when you're doing RTK. So first thing to note is this receiver is actually using a different correction service right now. So I'm going to reboot it and we'll watch it kind of come back online here. And notice in the upper left, it says status and then has HRMS and age. Those are really the three main indicators that I watch when I'm collecting data. Status is the fixed status. So you have, when you're doing RTK, you have RTK fixed, RTK float. When you're not doing RTK, it'll be either GPS like it is now, meaning it's not using any corrections. It's an autonomous mode. And then DGPS, which we'll probably flip to here pretty quick, is using a satellite-based correction service, which is in this case in the US is WAS. And so you'll notice the GPS, I'm only like a meter, 1.2 meters. As soon as it switched to DGPS, like it just did there, now we're in that sub-meter category. So it's an RTK enabled receiver, but not using RTK yet, doesn't have any corrections being sent to it. So it's acting as a sub-meter receiver. So DGPS status, next to that HRMS, which is the horizontal estimated accuracy. And that is 0.5 meters now. Okay, so 1.5 feet, 2 feet. And that's without internet or anything. That's just all satellite-based corrections. And you notice the age is like anywhere from 4 to 7 seconds. And that's because the latency just to communicate between the satellites is much higher than RTK over the internet. So when we connect to RTK, you'll see these values change quite a bit. You'll see the age go down to 1. You'll see HRMS really get snap down. It'll go from 0.5 to 0.0, 1 maybe or 2, which is in that centimeter range. And then the status will change to fixed, or you maybe see it in float. This is the sky plot of real-time active sky plot right now. So these are all the satellites that my receiver is tracking. We're using 35 satellites in my position, as you can see right here, and we have 48 in view. So that's a lot. Like if you ever did GPS data collection back in the early 2000s or maybe even 90s, I mean, this was just unbelievable. You'd be lucky to use, 5 satellites. So really lucky to be able to have this available to us today. And then below is the breakdown of the different constellations. So let's kick in RTK, right? So I'm going to go to differential, and this, depends on which app you're using. This app is, they're all kind of generally the same information that you put in. So I put in the IP address, port, the mount point is like a specific base station that you'll connect to, or network solution, and then your credentials that you have to connect. So I'm going to hit start streaming. And it's kind of doing that handshake right now. It's connected. And it's just going to run a timer while I'm connected. And watch the upper left where it says status DGPS and those other values. Because very quickly here, it's going to go to a fixed position. So there it switched to fixed. You see HRMS is a 0.006. So that's basically saying that it's a little over half a centimeter precision. Age is 1 second, which is what we want to see. And that's really what we're looking for, right? So that's that quickly. I changed my precision, my accuracy from my GPS receiver from a sub-meter receiver to a sub-centimeter at this point. Just because I have base station operating on this building, it's ideal environment. But that quickly, right? Going back to that L1 RTK conversation, this would be sitting here watching it still, right? Still get to that fixed position. And so the productivity on these things is just amazing because you can just break it open. I rebooted it right in front of you, so it took maybe 30 seconds or so to get a GPS position. Then you kick in RTK, and we're down to centimeter level, just under a minute. And now I'm ready to go map. So I would just leave this app here in the background. I'll just put it in the background and go to field maps. And in field maps, it's going to show my position. It's that blue dot there. and it gives me a indicator at the top, the GPS accuracy 0.6. And so that's reporting exactly what ETP was telling me. And fixed type, RTK fixed, station ID 1, that's just the base we're connected to. Age is 1, 2. And these values look great. So I'm getting sub-centimeter position in field maps on a mobile device using a Bluetooth, RTK receiver. And this has been a big improvement in the last 10 plus years now, going from these dedicated rugged devices, all-in-one handhelds that ran operating systems that were kind of obscure and required training, to an iPhone that everyone's used to, an app with a UI that everyone's familiar with or can easily learn. But you're still getting that high precision, high level of accuracy into the app to capture your assets. So I'm just going to collect a point and show you this is another important part of high accuracy data collection, is that we store those values that the receiver is reporting. We don't just want the latitude, longitude, and elevation. Those are probably the most important part, but we also want to see, what was the receiver doing when we captured it. So we have a record of the lat long altitude, record of the serial number, the fixed time. Then we have average horizontal accuracy. It's a great value. Average vertical positions, standard deviation. Um, and so you want to capture all this GNSS metadata, is what we refer to it as, with each high accuracy GNSS position that you capture. Okay, so I'm going to switch over here. And this is the dashboard for the RTK based software that we wrote. So this is the same software that runs on the mobile station, the static station, and can even be deployed into the cloud and relay multiple stations and create a network like this one is doing. We have many stations that are being brought in. But I'm in the Portland office, so I'm connected to this station, and you can see I'm just outside the office, so my baseline is great. 0.01 miles. And this is a great tool for troubleshooting, right? This has been very helpful over the years, getting really an insight into the users that are currently connected to the network or base station, and seeing, what base station are they connected to? Are they connected to the closest one, right? Because that baseline, that distance matters. Some people will specify the mount point they connect to and then go collect data in a different area and not realize it. So if I was connected to, the extreme again, like this station, I wouldn't be able to get an RTK fixed position. I'm too far away. The atmospheric conditions are very different. Um, and so having this dashboard to be see real time, like where users are connected to, do they have a fixed position? How many satellites are they tracking? Who it is and how long they've been connected. All of that is very helpful. And this software has a lot of different tools for managing user subscriptions and pulling in base stations from existing networks or other owned base stations. And it's really the differentiator with these, when you're setting up your own base station and operating it. Okay, I think I'm going to leave it at that. We went over a lot of stuff. I really appreciate you guys joining joining me today, and I hope you guys learned something. Um, that is always the goal. So let's dive into some Q&A. So we have, do you lose accuracy by just using a nearby course, or do you need a standalone base station? Um, no, you don't necessarily lose accuracy. I mean, you can, like, we have the Oregon network here, right? And they have a base station that is pretty close to me, just a few miles, I think it's 10 miles away. And if I connect to that, I'm going to see very similar values to what I just showed you guys. So not a big difference between that and the base station that I'm using here, but also it's because the Oregon network has up-to-date hardware. So they might not have, I don't think all their base stations support all 4 constellations, but I think most of them, if not all of them, support 3. And in most scenarios, like if you're, open sky conditions, it's not going to make it, you're not going to notice a big difference, right? So if you have a high quality network in your area that has base stations that are close to you, relatively close to you, right? 20 miles, something like that, then then you don't necessarily set up your own. But if there's a network like I pick on CRTN, I mean it's a very valuable resource, but it's not owned and operated fully by one organization. So you have a lot of different pieces of hardware in there. And so if you happen to be close to a base station that's GPS only, that then you would definitely get better accuracy by in more places by running your own base station, right? So that's a good example of where even if you have nearby Coors, you may want to set up your own because it's cost effective. It's going to make you more productive uh, and more reliable, right? You're not relying on them to upgrade their hardware and just waiting on them to do that, right? So that's a scenario where you'd want to set up your own, but not necessarily always. The other piece though is the cost, right? Maybe there's a great network in your area, but it's $2,000 a year per receiver, right? That can quickly add up if you're planning on using it for a long period of time. Okay, let's go with Mark. So Mark's question is, many of our utility field crews are still using RTK receivers connected to older base stations and state-managed networks like CRTN. Okay, yeah. Can you elaborate on how limitations at the base station level, such as single constellation support, affect overall accuracy, whether investing in our own modern base stations could yield better? So I think I kind of already touched on that. So specifically for GPS-only base stations, if you're out in the open, so your rover is in a spot like let's just say a parking lot, right, where there's not many trees, open sky, and you're close to the base station. Let's say you're 20 miles from that CRTN GPS only base station. It's gonna be okay. Like that's gonna you're gonna get a centimeter level position. It's gonna hold on to it. It'll fix just as quickly or very closely to what I just showed you. Where it's going to fall apart is when you're actually go out and start collecting data in different areas. So if you are collecting, water systems, kind of typical example for me, but if you're going in between houses, they've got trees and you've got a valve or a meter that you've got to get to in there, that GPS only position that your receiver is using because it's connected to a GPS only base station is going to fall apart very quickly. And I've had many stories with customers who were in that same scenario, and it's very frustrating. And so that's when you would should consider operating your own station that support all four constellations. Also, the additional frequencies can help as well because you'll be more productive, less frustrated, spend less time in the field, and it can pay for itself pretty quick. So that's yeah, that would be my suggestion. Another good one from Mark, is with the upcoming 2025 datum shift and the introduction of the new reference frames like the NETRF 2022, how RTK workflows, especially those relying on state, need to adapt? That is a great question. So what he's referring to is there is going to be a change in the official datum that that that's going to be the official datum for the US. So there's been many of those changes over the years. The current official datum is NAD 83 2011, and that is current one. That's what almost I should say almost all RTK base stations are referenced to. And so as soon as you connect to an RTK station, the coordinates that your receiver is outputting is now in whatever datum that base station is referenced to. So again, almost anywhere in the US, as soon as you connect to a base station, the coordinates coming from your receiver are referenced to NAT 83 2011. And just a side kind of topic real quick, most maps are, because of the base maps and imagery, are being used in WS84. And there's a shift between those two datums that need to be dealt with. And so that's something that people deal with today, where there's those two datums that are you're representing the same thing just in different systems, and you need to account for that. So with this new datum, we're going to be going from 93 2011 to this 2022 datum is going to be an interesting transition for sure. I mean, just because the NGS releases the new datum doesn't mean everyone's just going to move over to it immediately, right? That this stuff takes a lot of time. There's still a lot of people that aren't using 93 2011 that haven't moved over. They're using Coors 96 or some other flavor of NAT 83. And so I think there's going to be a, I think there'll be a lot of RTK networks that serve up both. I think there'll be mount points that will output 93 2011 reference coordinates and mount points that output the new 2022 datum. So that will provide a way to kind of transition when you're ready. Um, I think that's kind of the only way I see it going. And then it's up to individual organizations to migrate their data. So there'll be known, transformations between 92 2011 and 2022. So the actual technical like migration of the data is fairly straightforward. But large organizations with data in many places, like that requires a very specific and coordinated effort to move all your data from one datum to another. And so it's going to take time, and a lot of people will not do it immediately or might not do it for a very long time. And so these networks will need to be able to kind of work with that. And one more note on that is that you don't need to migrate all of your data to the 2022 datum in order to use it in the field necessarily. Um, Tools like field maps have features that allow you to kind of reconcile these datums. So you may be able to use the 2022 datum mount point and just tell field maps, hey, my receiver is connected to an RTK network reference to this new datum. Convert it uh, back to 2011 because that's what all my data is in, right? So that's another way to handle it. Okay. See, Ahmed, hi, I wanted to confirm the results you got for the rover accuracy, 6 centimeters for your phone, acting like a rover. Uh, and it's indoors. Um, yeah, it was actually less than six. It was point 0.6 centimeters, less than a centimeter, and it was Bluetooth connected to my phone. So my phone is inside with me. The GPS receiver was outside, just to be clear. So I am getting a centimeter level position to my phone for apps running on my phone, but the GPS receiver is sitting outside. That's why I was able to get that position. You cannot get centimeter level accuracy indoors with GPS. That's not going to happen. Okay, last one, I think. Maybe last two. For certain surveys and mapping projects, do you need to wait for certain times of the day in order to get solid connection to a certain constellation? No. Nowadays, plenty of satellites from all constellations. You saw I was using 35 out of 47 in view. I haven't, back in the day, they had tools, web apps that you could go in and see what the best time of day would be to go out and collect data. Because you'd have the most number of satellites, let's say at noon. So you'd go plan your whole day around collecting data at noon. I haven't done that in a very, very, very long time. That's totally unnecessary today, as long as your GPS receiver is capable of tracking all those constellations, right? GPS only, still don't think you need to do that. I don't think it matters much, but maybe then. Okay, Tom, take site photos and utilize QGIS to generate vicinity map with geolocated photos. GPS derived photos are not as tight as I would like. Okay. What product would be ideal to tighten up those? So this is the interesting one. So he's talking about taking photos, and most people know that photos have EXIF data now that contains GPS coordinates of the phone or device that you use to capture those photos. And so you can actually use it, like let's take an iOS device, for example. It could be Android too. You could use that device to take the photo as you normally would, but augment the device's position with a Bluetooth receiver. So there's lots out there. If you want a sub-meter position, um, it's teetering on, like there's some devices in the kind of the consumer level that will operate in open sky well. But if you want consistently sub-meter results, so you need to go with a like a Bluetooth sub-meter professional receiver that you would just, all you need to do is turn on, Bluetooth it to your phone, and it will automatically replace your phone's position. And every photo you take will have more accurate EXIF data. So if you want suggestions on receivers and that, or you want to kind of talk about that more, just shoot me an email. We can talk about it. Okay, last one. I think we're a little bit over our time here. Can you get any kind of data indoors, or is it only for outdoor data collection? Only outdoor data collection for GPS, for anything consistent, right? I mean, I'm not saying that a GPS receiver can't get a position in some buildings under some, but it's not even worth talking about. It's not a reliable data collection effort. There's other tools that are meant for that, and you can even combine them with GPS in certain scenarios. If you have a specific scenario you want to talk about, like you could just kind of summarize what are you trying to collect and how you want to try to use it, and I can help you kind of come up with a solution because there are solutions for collecting data indoors. Just depends on what you're doing. You can't just take a receiver and walk inside and expect it to work. Okay, so I think we got through all the questions. And so I think we're going to wrap it up. I really appreciate everyone attending and taking the time to listen to all about RTK. So if you have any questions, please reach out to my email address, and I will respond and try to help you out as best as I can. And we're looking forward to doing another one of these in the future. So thank you, everybody.